Alright, hey everyone, welcome to our first AIME video. In this video, we're going to be describing just some circle angle formulas and how those angles can relate to triangles and later quadrilaterals. But at the moment, we'll be focusing on triangles and going over some theorems that relate to said triangles. So let's start off with the definitions. If you don't know your definitions, you won't be able to understand any of this. So before we go, you guys need to be able to understand what all of these things are, from all the way from segments, endpoints, midpoints, and subtending, and a radian. Also, you need to understand what these types of angles mean. Right angles, or they're called perpendicular and orthogonal, acute versus obtuse, etc., complementary versus supplementary, and vertical angles. This stuff later I'll explain a little bit later, but one thing I want to discuss is a radian. So before we continue, we need to understand what a radian is, and I'll go more into detail in a trigonometry video. But at the moment, essentially, a radian is a degree measure. It's essentially like a way to standardize degree measures for like a circle. If you have a radius here, this is a really bad circle, I'm sorry. If you have a circle with radius r, and then you have a sector, the sector angle right here, theta, it will subtend an arc that has the same length as the radius. And so notice how it helps standardize angles, really. Because before we had to deal with 360 degrees as our standard, which is very, very arbitrary. There's no point of really setting 360. So now we can set it up where an angle is determined by the radius. And this makes calculations with angles, circles, even triangles more simple. For example, let's look at the circumference, which is equal to 2 pi r. All right. So a circumference, there's 2 pi times radius, right? So if it has 2 pi radiuses as the so another way of saying it has 2 pi radiuses. That's another way of thinking about it. And so if it has 2 pi radiuses, that means it has 2 pi radians, because a radian covers one arc length of one radius. So that means the angle of an entire circle is equal to 2 pi. So that's really one important thing of a circle, and half a circle would be pi, quarter of a circle would be pi over 2, and so on. Let's go back into the top right here. Let's go on to describing circle theorems. So we have angles formed by two chords with a common endpoint on the circle, which is going to be right here. And let me view out just a little bit so that things will be a little bit easier to see. Okay, so we have angles formed by two chords with a common endpoint on a circle. Essentially, it's going to be angle ABC. This angle right here is equal to arc length AC over 2. Essentially, like whatever this degree measure here, the angle right here is just half that. And this is a really important theorem for anything that relates regular polygons to regular triangles, and really any shape that can be surrounded by a circle, since now you can determine angles through just using arc lengths. Now let's go look into the second one, which is kind of similar to like how these ones work, but except now instead of choosing two chords that intersect on the circle, you're choosing two secants which intersect outside the circle. In this case, we have angle BAC. So this angle right here, that is equal to arc BC, which is A, minus arc DE. I'm just going to write DE right here to represent the points, minus arc DE, which is B, or beta, all over 2. It's half that. So it's alpha minus beta over 2. Now let's go on to the third one right here, which is we have a tangent line and a chord. All right. So we have the angle ABC. That angle, similar to like how the first theorem worked, where it was arc AC over 2. This one works here, where it's arc BC over 2. In other words, it's eta over 2. So another way of saying it is that you don't need two chords to use this formula. You can have a tangent line and a chord to do so. Now let's look at the fourth formula, which you can figure out when two chords intersect within the circle. We figured out when it's on a circle, outside the circle. Now let's look at inside the circle. And theta would be equal to alpha plus beta over 2. And using vertical angles, we know that this is also theta. And this angle right here is 180 minus theta. All right. So we have a plus, so remember, you just average these two arc lengths over 2, that the chord's like subtend. Now we can use these formulas to solve one of these problems, and I'll be solving exercise 10.2. Before I continue, these are not sourced by me. These are sourced from Art of Problem Solving Volume 1, The Basics, and they are found on page 89 if you have this book. I'll be only doing exercise 10.2. 10.3 you'll be doing on your own, and I'll put the answer in the description below. So we have points A, B, Q, D, and C lie on a circle shown with arcs B, Q, and QD are 42 and 38 degrees respectively. So, what is the sum of angles PQ? Let me zoom in closer really quickly. Alright, so let's get into drawing. So we have 42 degrees for this side, 38 right here. Alright, now those are really bad 38. So let's try, so one thing I first thought of was that I can figure out angle BAQ using the inscribed angle theorem. And same thing with QCD. So we have angle A is equal to 21, and angle C is equal to 19. Alright, now we need to figure out what is the sum of angles P and Q. That doesn't, I can't think of a way that helps us. That's AQ and CD aren't parallel. I don't think we can't prove that. So they can't be equal angles. Same thing with A. Well, alright. So what I'm going to guess is that we can't use those. Those are kind of useless. So let's try figuring out how we can work backwards from P and Q. So we know that P, it's two secants that are intersecting outside the circle, so we can do that. We can choose P is equal to BD minus AC over 2. And arc BD is equal to 42 plus 38, which is 80, minus AC, we don't know what AC is, over 2. Now we have Q is an inscribed angle, it's on the circle, so that's equal to AC over 2. So if we add them up, P plus Q, since it asks us for the sum, I noticed that the AC's over 2 cancel out, since it's minus AC over 2 and plus AC over 2. So what we're left with is 80 over 2, and it's equal to 40 degrees. And so we can figure out this answer not through finding P and Q separately, but finding the whole. This is a really important concept to know. You have to go directly at the answer. And you can put and substitute numbers for variables, and you can figure out, all right, which variables matter and which variables don't matter. In this case, I didn't even need to figure out P and Q separately, nor arc AC. I just needed to figure out, all right, arc BD is 42, is 42 plus 38, 80, and P plus Q is just half that. And now that I use both the theorem 1, the first and second theorem to solve that. Exercise 10.3 will now be using, I think, theorem 3 and theorem 4. And it works here. PA, PT are tangents to the circle. Find the measure of TXA if angle P is equal to 42 degrees. So angle P, this angle here is 42 degrees. Find TXA. And I'll be doing this on your own. So pause right now, and then when you're finished with this video, or you can check right now, check the description to find the answer. All right, now let's move on to talking about triangles. So triangles, there's a lot of special things with triangles. Really, we talk about the special segments and points in a triangle. So we have, now we have 4 different lines that we can draw within a triangle. One of them is the perpendicular bisector. The perpendicular bisector is essentially where you take any side of the triangle, you find the midpoint, so it splits it in half, and then you go perpendicular to it until you reach the other side. And if you do it with every side of the triangle, you end up with, they all meet up at the same point, which is termed the circumcenter, the point of concurrency. All 3 of them meet up at the circumcenter, and the circumcenter, the special thing about this is that it's equidistant from each vertex. And it makes sense too. Each line right here is just as far away from each vertex. It's the farthest away you can be from all vertexes, and the line right here, perpendicular, means that it doesn't approach anything closer to it. It means it goes straight parallel. Not parallel, but it goes as farthest away from the vertexes as possible. And if you can do that for every line, you can set up like, all right, if this is the farthest it can go for each vertex, that means each vertex must be equidistant from each other. That's a little bit confusing. It's understandable if you don't really get that right now, but I'll show you why it's important later, but I just need to go through this quickly. So we have a circle is equidistant from each vertex, and I draw a circle here just to show you like how this could work. So we have the perpendicular bisectors right here, P here, this here, with all the right angles in orange. But now if they're equidistant from each vertex, that means I could draw a circle around each vertex, and since they're equidistant, BP, PA, and PC are act as radiuses of this, quote, circumcircle. And that's why it's called the circumcenter. The circumcenter is the center of the circumcircle, which surrounds the triangle. Now let's go into its opposite counterpart. The opposite counterpart is the angle bisector. The angle bisector is essentially, you go to a vertex and you split it up so that the angle splits in half. This is kind of like the opposite. You split the side in half, and now you're splitting the angle in half, and then you draw a line until it reaches the other side. You do it for all three sides, you get the incenter. The incenter Q of triangle ABC is equidistant from each side of a circle. Before it's vertex, now it's side. And as you can see, we have AQ, BQ, and CQ. They all act as the angle bisectors, but you can draw perpendicular lines to the sides so that they are the radiuses of each side. And now you're going to get, and so now you are able to figure out that the incenter, right here, Q, is, and the incenter Q represents the total circle, which is the incircle. Incenter, incircle, circumcenter, circumcircle. And they're formed by perpendicular bisectors and angle bisectors. Now let's go on to the third and fourth ones, which don't have circles, but are really important since you can determine both length and angles. The median. The median is works similarly to the angle bisector, but instead of splitting the angle in half, you're splitting the opposite side in half. And if you do it for all three sides, you get a centroid, which essentially acts as a center of mass. So in the physical world, if you choose a centroid of any shape or any physical object, you can that's the balance point. You can balance everything on that centroid, and it kind of works logically too. If you're trying to split this triangle into two equal parts, right? And if you do it for every time from the vertex to the side, you try to split it into, you do it twice more for each side, then you choose a point where it's equal on all sides in two-dimensional space. And so, since it's equal on all sides, that's where the mass will all centers around. That's why it's called a centroid. And the most important part of the centroid is that the centroid R of ABC is 2/3 the distance from each vertex to the midpoint on the opposite side. So you take this median, the total median length. AR is 2/3 of that total median length. BR is 2/3 of BD. CR is 2/3 of its median length. Another way of looking at this is that BR is twice RD. That's another way of looking at it too. Now let's look at the final part, which is the altitude. The altitude is essentially you choose a line that goes from the vertex and you go down to the other side, but now you're making sure it's at a right angle to that side. All right? And if you do it for all three sides, you have a circumcenter. Or not circumcenter, orthocenter. I need to read off the actual graph, or actual chart. The lines containing the altitudes of ABC are concurrent at S. And the good news is that now you can create right triangles from the heights, from these altitudes. And with that, you can figure out areas of triangles and angles of triangles, because right triangles are so much easier to use than regular triangles, since you already know you can use Pythagorean theorem to determine side lengths, and you can already figure out what the other two angles can be most of the time, because you have one angle that's already determined. All right, so now let's get into let's just talk about just some trends with these shapes. So I have this isosceles triangle. This side right here is similar to this side, and we have the height right here. And notice I have drawn a lot of lines on it, but notice how they all are concurrent on this line right here. Why? It's because this line, the height, also acts as the median, right? It splits this line in half because it's an isosceles triangle. These angles are the same, so these triangles are actually, no, that's something a little bit later I'll explain. But essentially what this shows is that, all right, this is also the median. It splits it in half because since an isosceles triangle kind of like is already symmetrical, that's just a logical thing you can say. It's also the median. It's also an altitude since it creates a right angle here. It's also an angle bisector since it creates two triangles that are equal to each other. They're basically the same triangle, just reflected. And it also creates perpendicular bisector since it bisects here, and an altitude. So since this line right here acts as all four of these special segments, it acts as the circumcenter, the incenter, the centroid, and the orthocenter must all be on this line. And it's shown right here, where I have all 4 lines of each type that intersect right here on the centroid. And so you have the incenter right here, you have the circumcenter, you have the altitudes right here, the black lines, no, not the black lines, not the black lines, the orange lines, those are the orthocenters, and you have the medians, which I think are the green lines. All right, and that's the cool thing about isosceles triangles. Everything's on one line. All the special points, concurrency points are on one line. And then for an equilateral triangle, everything is in one point. There's a centroid, the circumcenter, the incenter, and the orthocenter. They're all located at one point. And it makes sense. Everything is equal to each other. Angles are equal, sides are equal. Thus, it makes sense why everything else should be equal to each other. Now, let's start looking at Now, there's some theorems that are related to this, but before we need to understand that, we need to understand how congruence and similarity works. And I'll go through this quickly, since these are theorems that you learn in geometry, and these are pretty simple. These are simple, relatively simple, and these are I'm just gonna go through them quickly. And so, congruence theorems: side side, side angle side, angle, and angle side. One thing to note is that how these theorems can be shown to be true is that, let's take side angle side. If you already know that two sides are equal, let's try pretending like, all right, let's see if I can make a different triangle with just this side and this side. How many possible triangles are there if I have two sides and the angle's already determined? Well, I can't change the length here, and the separation between them is same, so there's only one line possible between their endpoints. So there's only one triangle possible, so any triangle with this combination must be equal to the original. And this works for this logic works for every other, what's it called? It works for every other type of triangle. And congruence means they're the exact same. Same angles, same sides, same everything. And this works for any special segments that you draw extra to it. The altitudes are the same, the medians are the same, the angle bisectors are the same, and so on. Now let's go on to similarity theorems. Similarity theorems, similar triangles, same angles, different sizes. They're just related via ratios. And to show similarity, angle is one of the most useful theorems because if you know two angles, you can figure out the third one. Side angle side is similar to this one right here, but instead of showing that these two sides are equal, for example, you show that this side and this side, when in a ratio, is equal to this side over this side as a ratio. In other words, you're showing that these two sides are racially significant. And with that, you can figure out that, for example, this is shown right here. Triangles RST and XYZ, RS over XY, those are the two corresponding sides. RT over XZ, those are the other two corresponding sides. And the angle in between is angle R and angle X. If you can show that those two angles are equal to each other, then you can see that, all right, side angle side. And this is shown right here. AB over AD, AC over AE, and then you have angle A that's equal to angle A. Now, side, the two triangles are similar if all the ratio of the corresponding sides are equal. So you can show that all three sides have similar ratios, or same ratios. That means it's similar. Usually, this one is going to be the most important. Now let's get on to solving problems with that. Let's look at exercise 1118. So we have, let's just draw it out right here. So let's say we have 1118, TAPZ has TZ, AP, ER, and RE are the midpoints of AT and PZ. If AP equals 64, TZ equals 28, AZ equals to 46, find OI. Alright, so notice how we're dealing with the trapezoid. And that's the important thing about this too, is that we don't have to deal with triangles in this. We can just deal with a trapezoid. I won't be like fully on solving this, but I'll be showing you like how you can apply the theorems that we used earlier to solve for it. So we have, so let's try finding triangles here. Okay, so we know that TZ, RE, and AP are parallel to each other, so we can already figure out, all right, due to transversals. And this is the important thing here. When using parallel lines, think, all right, is there a line that crosses all three of them? Think transversals. So we have, let's try looking right here. So we have TZ and AZ. That's a transversal that crosses all three. And so we could say, all right, angle TCA is equal to angle OID, and angle or ZID and angle ZAP. Same thing with PTZ, similar to what's it called? Oh, OPA, because these are like alternate interior or something like that. Same thing here. And that's also equal to TDI, TPA. They're all similar to PTZ. So we can have some, we already found combinations of similar triangles. We have TOZ. Let's start with that since the first triangle I just saw. It's similar to the big triangle AOP. Let's try making sure that we match angles with angles. So that T must be matched with angle P. O is that matched with O, obviously, and then A, POA. And that's also similar to OID, OID. So we have T is matched with D, O is matched with O, and I is matched with A. And also you can look at this triangle right here compared to this. So we have O, IA, DP. So that's a really bad I, sorry. So we have TOZ, POA, and DOI. And now we have the similarity rules right here. Now we can figure out, all right, we need to figure out what OI is. And so we need to figure out how OI relates to AO. We can figure that out. And then we can figure out how AO relates to OZ. Do we know what the total AZ is? Yes, we do. So let's try doing, so we know that AO over OZ is equal to, let's use the numbers that we have here. AO is related to AP because those are part of the same triangle. Let me draw this again. I don't know why I canceled out. Oh, whoops. Hopefully that doesn't mess things up. AP over TZ, since they're part of the same triangle. So AP over TZ is equal to, I don't know why it keeps resetting. It's annoying as heck. And then AP is 64, right? 64 over TZ, 28. Is equal to, that's divided by 4, 16 over 7. All right, now we can relate AO and OZ, so we know that 7 times AO is 16 times OZ. And then we also know, and then let's try doing, let me choose a different color so it doesn't get too confusing. So let's try relating, actually no, let's try figuring out what AO and OZ are separately, since we know what the total is. AO is OZ, so I think we need to find AO. We need to figure out what AO is so that we can figure out what OI is. We need to work from there. So we know that OZ is equal to, we know that AZ is 46, so we know this is going to be, OZ is going to be 46 minus AO, right, because A. So now we can solve for AO via that. So we have 7AO is equal to 46 times 16. Oh god, it's really annoying to do. Oh god, I hate that so much, it's annoying. So we have 7AO from 46 minus 16AO. So we have 7AO plus 16AO, which is 23. So we have 23AO is equal to 16 times 46. So we know that AO is equal to 16 times 2. 23 divided by 46 is 2, or 46 divided by 23 is 2. It's equal to 32. All right, now we know what AO is. Now we can figure out what OI is from there on. So let me go right here. And so we can figure out what OI is by following the same process, comparing side lengths and going on there. And so that's one way to solve it really quickly. And then now we can figure out what. Now you can figure out from there on. And I'll put the answer in the description to see like whether you can get the correct answer. And if you want to do 1117 is also a good one you can try out, but I would not recommend it. So now let's go on to two proofs. Given chords A, B, and CD of a circle such that AB equals CD, show that minor arcs AB and CD are equal. So we have minor arcs AB and CD. So we can show that, let's draw a circle. If we have AB, so let's say C, gosh, it's annoying. AB and CD. Alright, so we have a center, and then we have A, B, C, D. It's always good to draw a center with a circle, because you can always relate things to it. So we have, oh my god, I swear to god, please, why does it keep resetting? Okay, so I don't think I need to go. Okay, so with AB equals CD, and then so your minor arcs AB and CD are equal. So we need to figure out what minor arcs are, how did that equal to, and how we can show that. Let's try working backwards. So the minor arc AB is equal to the angle that the sector comprises of, this angle right here. Same thing right here. So these two are equal. All right, so how can we show that those angles are equal? Well, we know that the center to A, center to B are equal since they're the radiuses. So, and these two are also the same radiuses too. They go from the center to the circle after all. So all four of these sides are equal to each other. And let's call the center O. It's a really bad O. Okay, hopefully you know. So we have AO. So now we can use congruency to figure it out, because you have sides that are equal to each other. And so we have three sides that are equal to each other, then we have angles that are equal to each other. So now we can figure out that COD is equal to angle AOB. And what does that mean? Well, that means that minor arcs AB and CD are equal to each other. Okay, that's one proof, and that's an easy proof right there. As long as you figure out that you can connect the radiuses, and working backwards, you can figure out that AB and CD are equal. Now let's look at one really important proof right here. If AB parallel CD parallel EF, show that 1 over x plus 1 over y equals 1 over z. So let's try showing it right now. So we have 1 over x is equal to, so we have parallel lines, and we have lines that cross them, BE and AF, for example. So I'm noticing, all right, transversals, and I already drawn them out really quickly. So we have the orange lines are equal to each other, and the blue and the purple angles are equal to each other. And notice how that works. So it's like we have EF, CD, they're parallel, and so we can figure out that, all right, that means CEF, BCD, ABF, and CDF. So let's try comparing them. So we have, let's try comparing ABF and CDF. So we can compare X and Z. So we have X over, let's see how we can compare both of them, which will help us. So we can choose two sides, let's say BF is equal to Z over DF. And that works for the same way right here. That works as y over, oh, why does it type it out? I think I accidentally clicked on my keyboard, which is equal to y over BF is equal to Z over BD. Because now we can compare EF to big side, little side, little side. And notice how, and the reason why, and so one thing you could ask is, why did I choose BD? Well, I'm looking at the bigger picture right here. I know I have to compare X, Y, and Z, and I'm trying to figure out, all right, if I can do ABF and CDF, and I can do I can do BEF and BCD, what do they have in common? I notice that they have BF in common. So like, if I can compare stuff to BF, that will help make my analysis easier. I don't know that for sure, but I'm predicting that it could help, because I need to show that 1 over x plus 1 over y equals 1 over z. And at the moment, I'm just showing that x equals z and y equals z. But luckily, thanks to that logical process and just thinking in the long term, I'm able to show that, all right, x over bf, I can figure out bf's are both in found equations. And since I need to figure out a way just to limit myself to x, z, and y, I can now try solving for bf. So I have x is equal to z over df times bf, or sorry, I have so I have xc, I think. Sorry, I'm trying to figure this out really quickly. Sorry about that, guys. So I'm trying to do quick maths, essentially. So dfx equals bf times z. So that means it would be x over z times df equals bf. and that is equal to BD times Y equals BF times Z, and so I have Y over Z times BD. All right, so now I have Z that's compared to each other, but wait a minute, I can't really compare that because that's a dead end. And that's the one thing with proofs. We have dead ends. We always come up with dead ends, since now the only thing I can figure out is, all right, well, Z is going to be canceled out if I multiply it out. And I get X times DF is equal to Y times DZ, which is actually a pretty neat theorem, but it doesn't help us there. So, all right. Okay, since I compared X and Z, Y and Z directly, let me try doing X and Y. Let's try comparing them together. All right, I noticed that they both have purple and orange angles. So I'm like, all right, they must have similarities. But lo and behold, we have ACB is equal to FCE. And if I draw that out, that would be equal to, so we have AE, oh gosh, okay, so we have X over AC is equal to Y over CF, right? Because I'm comparing two angles that have that right here. So we have okay, so okay, that's really annoying. Huh. I'm gonna see if okay, so I'm not really getting anywhere there, but let me see if I can make more equations using X and Z. Or Y and Z, I suppose. Oh, I could say that X over AC, X over AF is equal to Z over CF. And notice right there, I can Z over CF, sorry. And then I can compare both of them to show that, all right, X equals Z, X equals C, and so we have Y equals over CS, so we can do that. If we do X over Y, so we can show that X, this is just going to be some quick algebra. I can compare these to 1 over CS, so I can do X over Y times 1 over AC is equal to X over Z times 1 over AF. All right, so now I can, okay, this has the same problem as before. So I think now I'm like, all right, so I'm just going through a bunch of dead ends. Like, I can't really figure out a proof. And this is a problem, this is the thing with proofs too. You go through a bunch of dead ends. But the thing is like, all right, if I can find a similar dead end here, that means there must be a way to solve this. I'm so close on the prefaces, I'm so close to reaching the answer. So let's try going back here. X over Z df is equal to Y over Z times BD. So BD and df, they both have compared to, they both have BF. Actually, no, one second. We could actually compare. We could do BF minus DF. Okay, this is getting really confusing, and I'm just going to clear out everything. And let me just do draw. Let me just do stroke eraser so that it makes things so much easier. So let's try maybe doing the other one. That's because I want to continue that, and I remember that. I forgot the other one. So we have X over AC, and then Y over AC, and then we have, oh, sorry, let's do, so we have X over Z times DF is equal to Y over Z times BD. Let's try doing this as BF minus BD, or DF. So we know that it's going to be, we know this is going to be turning into, oh god, this is really annoying how it cancels out every time I try to move. So I get X So I get x over z plus y over z df, since I can distribute it. So we have x plus y over z times df is equal to y over z times bf. And we know that bf is all equal to all of this stuff. So we know that's going to be equal to, let's say, oh, I got it. So we can say that's equal to, draw. I can show that that's equal to x over z times df. Since going back here, yeah, okay, it looks like if I hold it on for too long, so bf is equal to x over z times df, and so we can compare that back. So now let's get back into some equation solving. So now we have x over z times df, df's cancel out, and what you have with is x over z plus y over z is equal to xy over z squared. All right, now the z won't be able to get canceled out, so let's try multiplying by z. So we have x plus y is equal to xy over z. If I divide by xy on both sides, I can get 1 over z, right? Because that's one way to get 1 over z. If I do divide by xy here, this cancels out to become 1. xy over x plus y over xy, that becomes 1 over y plus 1 over x, because the y's cancel out on one side and x cancel out on one side, so you get 1 over x plus 1 over y is equal to 1 over z. Awesome. So, what was the point of this? I spent about 10 minutes of my life just trying to prove this one thing that was given from an AOPS book. Why? Because I just want to show you, like, these proofs with similar triangles, they take time. And this is just one strategy you do. You go through different paths and trying to figure out, all right, in the long term, this could lead to that. And trying to choose, like, decisions that that you predict will help you in the future. And sometimes those decisions don't work out. I tried doing AC times BF. I thought it was a dead end. Tried to do another way. That was a dead end too. So I went back to it and I was like, all right, I tried a new way, BF minus DF. And was able to compare all of this right here through a bunch of algebra. And I feel like there's an easier way to do it. But what I'm trying to show you, the final thing is, like, just keep trying to look for ways to relate everything to each other and try to be like, all right, is there any ways I can make this simple? Any ways I can get closer and closer to 1 over x plus 1 over y? And I was like, all right, I can cancel out df, I can cancel out bf, and all of this can help me get to this final solution where I was get to 1 over z. I knew I had to divide 1 xy, and so 1 over x plus 1 over y equals 1 over z. Now, that's all the stuff I'll be talking about similar triangles. If you want to try to exercise 11-17, I'll put that also as the answer in the description. But also, I'm also going to show you these two problems right here. These answers can be found. This is AMC 12A 2016 problem 12 and AMC 12A 2014 problem 10. I won't go through these since there's really good solutions already on AOPS's website, but they will follow similar ideas that I'll give right here. But the main issue is that for this problem right here, for these problems, we still need to go over two more things. And, one thing. And one thing is going to be going over two theorems that relate back to these triangles here. And I need to discuss them before I move on to talking about those problems. They're called the perpendicular bisector theorem and the angle bisector theorem. All right? So, the thing is, like, now notice how these are related to circles. We can figure out, all right, we can use the angles that are found in those circles to figure out, like, all right, we can figure out, all right, so there must be some way to show that perpendicular bisectors right here are going to be useful in the long term. So I'm trying to... So let's go over the angle bisector theorem first, because that's the more simple. That's going to be a more simple one and relates more to similar triangles. The angle bisector theorem is that, let me get out a triangle. Let's choose a shape. Okay, this is going to be really annoying. I'm not sure how I can, I don't think I can make scaling triangles. Well, okay, well, what otherwise? So we have, let's say we have an angle bisector, let's say like right here. This is a really bad angle bisector, I'm sorry. But let's say we call this A, B, C, and we have AD as our angle bisector. We can show that out of all of this, DC over AC is equal to BD over AB. That's the angle bisector theorem, where you just take the two sides that are split up and they can be compared to. But this does not mean that these two are similar triangles, and it could be plainly obvious, because if we assume that angles B and C are different, then we already obviously know they are similar triangles. But this relationship comes up and relates to trigonometry. That's a proof, but I just want to show you this angle bisector theorem right here, and this is going to be really important when you try to apply things to everything else. And okay, that's really the only thing you need to know. And this is the angle bisector theorem. There's no really any perpendicular bisector theorem. There's probably something similar, but it doesn't really show up for now. But that's all really I need to tell you about the angle bisectors. There's medians and altitude theorems, but they are more complex and they relate to, I can't really just show you them. I need to talk about them a little later. Now I'm done talking about congruence and similarities. I'm going to talk about two more things before I get into, and this will be talking about trigonometry. So, trigonometry, sine, cosine, tangent, secant, cosecant, cotangent, sine squared plus cosine squared equals 1, sine squared equals 99x. These are all definitions that you need to know, and I think one of the things I could teach you is the secant is 1 over sine, cosecant is 1 over cosine. Oh no, sorry, I messed this up. Cosecant is 1 over sine, secant is 1 over cosine. I should have put them in a different order, I'm sorry. And cotangent is 1 over tangent. Is over tangent of x. So, and sine squared plus cosine squared equals 1. Sine squared equals cosine 90 minus x. These are really important, as you can relate sine and cosine to a number, and you can relate cosine and cosine to each other. And so these are just a quick guide through trigonometry. And another thing you need to figure out are the 45, 49, 90 triangles and the 30, 60, 90 triangles right here. And these are something that you should know through geometry class right here. X squared to 2x, x squared 3x, and 2x. And these are basically just showing, like, if you have value, let's say 2, this value here is 2 squares of 2. Then I'll do 1121 just to apply this one right here. Sine x equals cosine 90 minus x. So we have find the smallest positive angle, such as sine of 3x is cosine 7x. So we can do sine x. So we can relate sine x is equal to cosine 90 minus x. So we have cosine 90 minus 3x is equal to cosine of 7x. So we chose like the value here, then we just subtract that from 90. So we have that. And then now we have cosines on each other. So these two, the numbers inside the parentheses must be equal to each other. So we have 90 minus 3x is equal to 7x, and x will equal 9, because plus 3x, 10x, and then 10x, and then 90 divided by 10, x equals 9. And so the spot is positive angle x, so x equals 9 degrees. And then 1122, I won't be showing you that answer. I'll show the answer at the bottom of the page, but it says find AC at triangle side AB if angle A is equal to 90 degrees, so right triangle, secant B is equal to 4, and AB is equal to 6. So what you need to do is figure out what secant represents using that SOHCAHTOA. And secant has its own, like, remember, it's 1 over the sine of x. It's 1 over that opposite over hypotenuse. So secant is equal to hypotenuse over the opposite side of angle B, which is going to help you a lot to solve it. Now, the final topic I'll be going over will be triangle area formulas. So we have, these are 4 major triangle area formulas that you must memorize to help you figure it out. And we have the base times altitude over 2, which is the one that you most likely learned in school. One where it's like base times h height over 2 is equal to the area. Area is 1/2 base times height. Now the next 4 ones are relatively new ones, but if you went to geometry, you should probably recognize some of them, especially this one and this one. So this one, side A times side B times sine angle of 1/2 of angle C over 2. Essentially, let's take a triangle. Let's say call this C, angle C, and this is angle A, this is side B, or side A, side B, angle C. The area of the triangle is 1/2 AB times sine of C. That's it. You can figure out the area of an angle of a triangle just through that. And then we have another way is Heron's formula, which is square root of S times S minus A times S minus B times S minus C. But you're probably going to ask, what is S? What is S? S is a semiperimeter, and the semiperimeter is just half of the total perimeter. Remember, a perimeter is just the sum of all the sides. So we have S is equal to A plus B plus C over 2, and you have area is equal to square root of S times S minus A times S minus B times S minus C. Now, these two ones right here, they use the inradius and the circumradius. Remember those two special lines? Well, now you can figure out the inradius and the circumradius based on using each of those. And the area of a triangle can be determined by the inradius times the semiperimeter, or the multiplication of the sides divided by 4 times the circumradius to find the area. And these are just two like smallish formulas that are not going to be applied a lot really until they really will be. They will be in special cases, but the 3 most important ones are this one, these two, and this one. And that's really all I really need to talk about area triangles right here. But I'll be doing exercise 1125, and that will be the end of the meeting. But I want to talk about before I go, I want to talk about the problems that will be showing up here. So we have exercise 1125. Tangents from point C to circle O are extended from AB such that AB is tangent to O at X. If the perimeter of ABC is 50 and area of ABC is 100, find the area of circle O. Alright, this is really confusing. I have no idea what's talking about. So let's get into it. I won't be solving the entire thing. Actually, I might. But actually, no, I won't. I'll let you guys figure it out from there, but I'll be showing you how these formulas can be applied. So we have tangents from circle C to circle O are extended to AB, so AB is tangent to O at X. Okay, Okay, so we have a circle right here, and then we have tangents from point C. Let's call this C. They are tangent like this circle O, and then they're extended to A and B such that AB is tangent to O at X. So if the perimeter of ABC is 50 and the area is 100, find the area of circle O. And this is where we have the area of circle O. Notice, let's try to figure out, alright, what is circle O? If you notice how it's tangent to all 3 sides, you automatically think, alright, it's a triangle that surrounds the circle, or it's a triangle, or it's a circle inscribed within a triangle. It is within the triangle, and so it's the in-circle. Circle O is the in-circle of triangle ABC. And so, now you can figure out the in-radius of it. So this is R, and we know that the area of the radius is R times S. So, the semiperimeter, we know that the full perimeter is 50, the semiperimeter is half that. We have 25 divided by 2, we have 25 times R is equal to 100, the area of the full triangle. The triangle's area is 100 after all. And so we have R equals 4, 125 is 4, and now we can figure out the area of circle A by using A equals pi R squared. So thus, the area of circle O is equal to pi times 4 squared, 16 pi. So that's if you knew that formula, you could figure it out easily. And a lot of problems could be like that. And this is just showing one small application of that. If you didn't know the formula, you would be stuck. You would have to go through a long, drawn out proof to show that, oh, that's an incircle, and that's how the incircle's area can figure out all this stuff. But now let's get into, so now that's all I really need to talk about right here. And so now that's all the stuff that I really need to talk about. Now I'm going to talk about all these AMC problems I have to the right. So I have this right here, and also I have the angle bisector theorem, since this will be used to help you solve this. So you have triangle ABC. I got these from AMC 12, problem 2016, problem 12, and AMC 12A, 2014, problem 10. You can use these. You can use this like processes that I used here, all the formulas, all the stuff to solve these equations. Albeit you'll have to use some other logic stuff, and if you get stuck on them, there's a solutions tab on AOPS's website. AOPS will be your best friend in this case, since they have all access to all AMC problems, and this is how I have access to these problems. So you can figure out, you can go to search up AMC 12A 2016, go to problem 12, this will be here, and try to solve it using the stuff here. And if you get stuck, use a solution. And it's the same thing here. The bottom here is AMC 12A 2014. Then I have more here. All triangles. What is the area of trapezoid DBCE? What is the area of a shaded region given this 8 times 5 rectangle? So you can figure out just by using triangle formulas to figure out all of this stuff. So we have AMC 12A 2018 top here and AMC 12A 2016. So that's all the similar triangle stuff. And the reason why I'm using AMC problems is because I need to set up the basics before we get into the more complicated stuff, which will occur in next video. I will be expanding on trigonometry, and I'll be expanding on triangle area formulas, so that we can get into more like how circles relate to all of this stuff, and to show and to prove a lot of these formulas, and to solve more of the complex stuff that arises. But the thing is, I need to set up the basics, and you need to know how this works out, and to show like some smaller problems that help out with this. So regardless, that's all I have for today. Thank you so much for watching this video, and if you want to see more like in person, like how to solve them, you should check out the Lubbock Math Club and join Lubbock Math Club. It will provide you a Google Classroom link, and my friend Jeff, he will be teaching and be going over problems with it. I'm here to teach the concepts with these videos. But regardless, check out Lubbock Math Club in the website in the description below. The website will be there along with the Discord link so that you can get access to the Google Classroom. But that's all I have for today. Thank you so much for watching this first video lesson. Later, in this week, I will be posting another video that will be talking about trigonometry. That will be focusing specifically on this stuff and be going into more detail over just like trigonometric functions, how they relate to areas and how they relate to sides. But that's all I have. Thank you so much for coming, and I hope you have a great day.